Greetings, AP Chemistry. We are almost done with our solutions unit. We are just wrapping things up with titrations. So titrations, I would say, are much like the Spec 20, one of the essential lab techniques that you need to know to become a chemist. So a titration is kind of like a chemist's bread and butter. They use it in tons of different industries, even in like cheese making. So if they're making a batch of cheddar cheese to know if their cheese is at the right point, they run a titration of the whey that comes off of the cheese, and then you know that your cheese is at the right point for your flavor that you want. So it's a super critical skill that you need to have. And we're going to kind of go through what you need to know to learn about a titration. So what a titration is it is a technique where a solution of a known concentration or a known amount of chemical, most of the time it's a solution, but sometimes it's a solid, is used to determine the concentration of an unknown solution. So the idea is that you take something that you know to analyze something that you don't know the concentration of. And there are some terms that you need to know when we're talking about titrations, so that you can, kind of sound like you know what you're doing. So the first thing that we talk about is there's a name of something called a titrant. The titrant is your solution of known concentration. And I would say 90% of the time, that's the thing that's going to go inside your piece of equipment that you're going to use for the titration, which is called your burette. Sometimes you put your unknown solution into the burette, but most of the time it's your known solution concentration. Your analyte is the thing that you are trying to figure out the concentration for. So that is your solution of unknown concentration. In a titration, you hit something called an equivalence point, and that is the ending of your titration. It is the point in the titration where the moles of your analyte have completely reacted with the titrant, and you have perfectly hit the stoichiometric ratio where they have reacted together. And it goes with your stoichiometric ratios from your balanced equations. And that point is where you have equivalent amount of moles that are needed to react. So it might not be like exactly equal moles, but it could be a perfect 2-to-1 or 3-to-4 ratio or whatever. But that is the ending of your titration in theory. To mark that, you need to show something called an end point. Now, the end point in a titration is a point where you usually set a color change to happen to let you know that the chemical process that you're testing is over and that you've hit that point where the moles are equivalent. If you are smart and do a good job, you set your equivalence point to match up with your end point. If you are not good at your job, your end point happens not at the equivalence point, and then you think your titration is over, but it's actually either not done or you still have more to go with your titration. So if you're setting up your titration, you are going to want to set your endpoint where a color change happens with the equivalence point where you get your equal moles. Now, not all titrations require an endpoint color change, but it's the easiest thing to happen. You could use more complicated pieces of equipment, which we'll get into later. But the easiest thing to do is just set up your endpoint to happen at your equivalence point, and then you don't have to worry about it. For your titration, your most common piece of equipment that you're going to use is something called a burette. Now, a burette is a very precise chemical delivery system. And it is set up, and I'll show you in the next slide, with milliliter graduations and then 1/10 of a milliliter graduations in between. So it's incredibly precise because you can get things down to 2 decimal places when we're talking about volumes. The burette loads from the top, and when we get into the lab, I will actually show you how to get that prepared, but it loads from the top, and then you let chemical out from the bottom, turning this little valve at the bottom, which is called the stopcock. And what happens is there's a hole drilled in it, and then depending on how much you turn it, you can let out a little bit of liquid at a time or a lot. And so usually you put your titrant of your known concentration in here, and then you drip it down into an Erlenmeyer flask that contains your analyte. And so during your titration, you will have this thing set up into what we call a burette clamp. Like I said, we're going to be doing a lab with this, so you're going to see this whole setup. But you have it set up in a clamp, and then you swirl, you let the liquid in and kind of swirl your analyte as it mixes with your titrant. Okay. Now, reading a burette is a little bit different. A burette lets you know how much liquid is out of it. And so what happens is at the top of your burette is the 0 line. So that tells you that you have nothing added. And then what happens is as you let liquid out, it slowly drops. So it goes from 0 to 1 to 2 to 3 to 4. It's very much a different kind of piece of glassware that takes a little bit of practice reading. So what I'd like you to do here is see if you can kind of estimate what you think the initial reading of your burette is and your final reading. And the reason why we do this is because if you're running a titration, it sometimes is not necessary to reload your burette to 0 every time. When you set your burette up, a lot of times what you just do is you get it to a reading, take the start, take the ending, and then you can just keep on going with your ending reading as the next reading that you take. So if you take a look here at your initial reading and your final reading, take your best estimate as to what they are saying, and then I will kind of show you what they are. All right. So in my best estimation, I would say that this burette reading is 9.5. So here's the 9.5 mark, plus an additional 0.1. And then this is kind of a judgment call here. I'd say it's maybe not quite a 0.05, but it's not. If you look at the bottom of the meniscus, the bottom of the meniscus is also not at the 0.6 line. So I estimated this to be 9.65. It is not 10.4. So this is not like a graduated cylinder. You read how much is out, not how much is in. Okay, so our titration started at about 9.65. If you look at the final reading here, here is 24. Here's 24.1, and we're about halfway through, so I said 24.15. So what that means is from here to here, we let out, in this case, 14.5 milliliters. And when you do a burette reading calculation, you do the final initial, the final minus the initial. What they're going to ask, and I've seen this happen on a lot of exams, is that they'll ask you what kind of data you need to collect. You don't need to collect the volume added. What you need to collect is the final and the initial volumes, and that will give you the amount added. So the actual data you collect is the start and the ending volume. The volume you use is actually a calculation. Okay, so it's kind of different, but we know that we're dropping. So this measurement on your burette is going to be higher, and then the 24 is going to be lower. Most burettes contain either 25 milliliters that they can measure or 50, depending on the burette. They're very expensive. They're like $80 a piece because they are an extremely precise piece of equipment. When you set up a titration, I told you that the endpoint was super critical. And the reason why is because the endpoint gives you a color change that happens usually very quickly to let you know when you have your titration complete. And so what you need to do is you need to set up the point where the color change happens with the point where your moles are equivalent in your titration. So what we're doing, like I said, is adding chemical in to react with a known chemical. And then those two things, once they are equal, we want to see that color change happen so that we know to stop our titration. Now, you could use a piece of equipment like a pH probe or an electrical conductivity meter or something like that. But in terms of having real quick data, the easiest thing to do is to look for something that changes color. And you get color change happening in one of two ways. Either you have a reactant that's colored and that shows up or disappears. The color either shows up at the equivalence point or it disappears at the equivalence point, and that will show you an endpoint. An example of that would be something like potassium permanganate. It's got a purple color, and if you do a titration of it and you try to get rid of it, it slowly becomes less purple. And when the purple color is gone, then you know your titration's done. The other thing you can do is you can add an indicator. Now, indicators are sensitive to pH changes or the acidity or basicity of a solution. And a lot of times when we do titrations, we're titrating an acid or a base. And so what happens is you can catch the color transition of an indicator to show you what is happening at your equivalence point. And here are just a couple examples. So this is 4 indicators at a pH that is lower This is bromocresol green, phenol red, bromethymol blue, and methyl red. And what happens is if they transition to a higher pH value, they change their colors. So when we're setting up a titration and we're talking about trying to figure out an equivalence point, what we want is we want the color at the equivalence point to be a combination of these two colors. So for instance, bromocresol green is green, and I believe if I'm not mistaken, it starts off as yellow. So what we are looking for is a green color to hit the equivalence point. So we want our equivalence points pH to happen where bromocresol green is green. Another example is methyl red. So methyl red is kind of this yellow color at a higher pH, and it's red at a lower pH. So the transition color for that is an orange. So we are looking for a light orange color to show up, and that lets us know that we've hit that equivalence point. So what you have to do and be smart about is setting up that color transition to match where you want your endpoint, or where you know your endpoint is going to be. And that's a little bit challenging. And we're going to get into acids and bases in a later unit, and then you will become professionals at this. Okay, so when we solve a titration, there are two ways to figure it out. They get you the same answer, so it's honestly a personal preference. One of them is through stoichiometry, and stoichiometry will never fail you. The other way is by using a variation on our dilution equation, which is M1V1 over N1, and N is the coefficient of your substance in the balanced equation, equal to M2 times V2 over N2. So what I'm going to do is I'm actually going to give you guys a practice problem, and then I'm going to solve it both ways and show you how to do it in both circumstances. So here's our titration. We're going to have hydrochloric acid and calcium hydroxide mixing together to make water and calcium chloride. So if you read the problem, says 38.4 milliliters of 0.5 molar calcium hydroxide is required to completely neutralize 50 milliliters of HCl. What is the molarity of the HCl that was titrated? So the idea is that I don't know what the molarity of this is. I do know how much it took of this calcium hydroxide. And so if I know the volume, I can figure out the molarity of the unknown. And there's kind of two ways to approach that. There's a stoichiometric approach and kind of a shortcut approach. So I'm going to go through those examples now. If you want to give them a try, you can pause the video, but we're going to kind of work through those together. Okay, so I have here my balanced equation, 2HCl plus calcium hydroxide turning into 2 waters and CaCl2. So from the information that I'm given in my problem, I know that I have 38.4 milliliters of the 0.5 molar solution here for the calcium hydroxide. And I know that it was 50 milliliters of my HCl. So what I need to figure out is I am trying to figure out, in this case, my molarity. I need to figure out, in this case, moles of my stuff divided by liters of solution. So the way that this titration works is that I can figure out how many moles of my titrant it took to neutralize this analyte, and then if I know the moles, I can figure out the concentration. Okay, so I'm going to start off my stoichiometry with the only thing that could actually get me moles, which is the volume times the molarity of my calcium hydroxide. So I have 38.4 milliliters of my calcium hydroxide times the molarity, 0.5 moles of calcium hydroxide over 1,000 milliliters. Like I've told you a bazillion times before, the moles, if I get them by taking molarity times volume, I get the moles. So here I've got moles of calcium hydroxide. Now I'm going to solve for what I'm solving for. Got to get rid of my moles of calcium hydroxide. And it's 2-to-1 ratio. Okay, so if we think about units, milliliters and milliliters go away, moles and moles go away. And at this point, I'm in moles of HCl. My units I'm looking for are moles per liter. So I need to actually stop my problem here and get my moles of solution. I've got 0.0384 moles of HCl, and they are held in a 0.050 liter amount because I had 50 milliliters of my solution. So that's 0.05 liters. If I do that and I do the division, I get 0.768 molar HCl, or 0.768 moles per liter for my concentration. So again, the idea is that I take something of a known concentration and figure out how many moles it has to get rid of this chemical. And so I had to neutralize 0.0384 moles of HCl, which were contained in 50 milliliters. So this is my concentration. Now, the other approach is the M1V1 over N1 approach, and it follows the same balanced equation. And with this, you just have to make sure that the one chemical is your M1V1N1 and the other one is your 2s. So I'm going to start off with what I know to start off with. So I have 38.4 milliliters times 0.5 molar. And this is all for my calcium hydroxide. Now, the N1 comes from the coefficient in front. So my calcium hydroxide has a 1, so I'm going to put 1 mole of the calcium hydroxide here. I'm just going to put 1 mole. The units aren't super important in this. In the stoichiometry, they are. In this one, not so much. On the other side then, I'm going to have HCl's information. So it was 50 milliliters was the size of the sample that I was analyzing. I do not know the molarity of that, but I do know that in my HCl, I have a coefficient of 2, so I'm going to put 2 moles there. And now it's just an issue of solving for the algebra. So I'm going to multiply both sides by 2 moles over 50 milliliters to get my units to kind of cancel out. Oops, I mixed that up. Sorry, my bad. There we go. Pretend that never happened. These will cancel out, and we'll take 2 times 38.4 times 0.5. Make sure you put that in parentheses when you put that in your calculator, and then divide it by 50 times 1. When you do that, you get the exact same answer. So it's 0.768 molar for your M2. So either of these approaches are fine as long as you don't forget that you need these coefficients here. You have to have them in. And I would say on my side of things, I want you to show them even if it's 1-to-1, because otherwise you get real sloppy and you start to forget. So both of these work. It is a personal preference as to which one makes most sense to you. What we're going to do is we're going to be getting into a lab. We're going to take a titration of a soda, and we're going to try to figure out the concentration of the acid in that soda. So please give these questions a try. If you have any questions, please make sure you get them answered, and good luck.